So we will. So you should have a link in the classroom itself to review the recordings. I'll verify that to make sure it's uploading automatically. You have a recording of another class as well. What we're going to do is we're going to shift a little bit. And so we'll be looking same material, but we're just going to pull it from a different site tonight. And we'll see what's up with the other site. So we've been talking about circuits and DC circuits. Actually, let me stop that and share something else right quick. Okay, can you guys see that series DC resistive circuits? Perfect, perfect. So up to this point, we've been talking about, we started off with a little bit of math. We looked at everything from exponents to scientific notation, engineering notation, looking at some prefixes, and then getting into this notion of batteries and looking a little bit at resistors and the value of resistors. And we began to talk a little bit about series and parallel, and I think it'll start becoming more clear as we get into this presentation, series DC resistive circuits and voltage dividers. And so what that means is, series, one path for current to flow. And remember, as we were talking about series circuits, we said that current is always common in those series circuits. The same current is flowing throughout the entire circuit. There's that one path for current to flow. And so series, DC, direct current. And so we're talking about, battery, current's always flowing in the same direction. It's not alternating. You guys are familiar with alternating current, direct current. DC just means that my current flow is going to be in the same direction at all times. Resistive, meaning that these circuits only have resistors in them. That's the only component we've really talked about at this point. We will begin to add other components later, but to start off with, this is the great place to start. Series DC resistive circuits, and then voltage dividers. This is and voltage dividers. Well, we're going to see what that means. We're going to talk about what does it mean to have a voltage divider. Couple learning objectives, looking at the schematic. Select a statement which describes a total opposition to the circuit. So how do we calculate total resistance? Given several values, if I'm given current, total current, voltage applied, how do I figure out my resistance total, or how do I calculate current total if I'm given the other two components? How do I combine the resistors and calculate the voltage drops across those resistors? Power, how do we calculate power? And then also select the primary purpose of a series resistive circuit. So here we have a series resistive circuit. We've got our supply. So on the left-hand side, we've got a battery here that is going to push electrons, negatively charged electrons, away from the negative side of the battery, draw them toward the positive side of the battery. And so I've got current flow that is clockwise around this circuit, starting negative to positive, it's clockwise. I've got a resistor here of 8 ohms. And so I could calculate my resistance if I wanted to. I could come in and I could figure out what is my total resistance. I could figure out what, all those different components. Here, what they're really looking at you to see is that, notice this RINT. Really, this is probably going to be one of the few times that we see this. It's talking about even a resistance internal, resistance load, right? What they want you to see, really, the takeaway here is, notice that we've got one path for current flow. This is a series circuit. The current is only going to flow from negative to positive. It's going to go down through the load, and it's going to come back to this positive side of the battery. Remember, we got this chemical reaction that is taking place inside the battery that causes these electrons to be separated out, an abundance of electrons on the negative charge, an absence of electrons on the positive charge. We said that likes repel those negatively charged electrons. If I'm an electron sitting up here, I'm repelled from the negative charge of that battery, and I'm drawn toward the positive side. Current is the same no matter where I measure it in this entire circuit. It's going to be the same. Now, let's take a look at a total resistance. We've got 3 resistors, R1, R2, and R3. They're in a series circuit. We've got current that's flowing through this circuit, once again, in the clockwise direction. And notice the current has to flow through, one path current flow, has to flow through R1 and R2 and R3. So the resistance of R1 plus the resistance of R2 plus the resistance of R3 makes up our total resistance for this entire circuit. Pretty easy, right? All we have to do is add them together. Our total resistance is just R1 plus R2 plus R3. The Rn just goes to show you that if we got a series circuit, as many resistors as I have, if they're all in series, I just add them together. R1, R2, R3, R4, R5, R to the nth, whatever it may be. You can hear you can see here we've actually put in the values: 1 ohm for R1, 2 ohms for R2, 3 ohms for R3, for a total of 6 ohms. My resistance total would be 6 ohms. Pretty straightforward. Not difficult at all for a series circuit. Just add them together. Now, if we want to use Ohm's law, and we said Ohm's law is that relationship that exists between voltage and current and resistance. Well, we can use Ohm's law and calculate our current because we have our voltage, right? We had a total voltage of 6 volts. We now have our total resistance of 6 ohms, right? It's easy to start with the formula: voltage is equal to current times resistance. I can solve it so that I get current, you see, is equal to voltage divided by resistance, my 6 volts divided by my 6 ohms, right? So that's what I have here: 6 volts divided by 6 ohms for a total of 1 amp. So I've got 1 amp of current that's flowing through this circuit. And no matter where I put my ammeter, negative side of the battery, I'm going to get 1 amp. Top side of R1, I'm still going to get 1 amp. Between R1 and R2, 1 amp. R2 and R3, 1 amp. No matter where I measure, because current is common in this series circuit, there's only one path for current to flow, I'm going to get 1 amp. Now, you guys that familiar with taking measurements, current measurements, we're going to talk about this a little bit later. We're going to see this, but anybody take a stab at what I need to do if I'm going to measure current in this circuit? I have a multimeter that, I switch to amps, and I'm going to measure current. How would I connect it in this circuit to measure the current?
From negative to positive, wouldn't you? You hook the one side on the negative side, you red on the longer line and the black on the shorter line. because it's in series, so it's all gonna go in one direction. So that's the way you could get it.
Okay, so one of the things that I need to make sure that I do, and the key piece here is when I take my ammeter, in order for me to measure the current that's flowing through this circuit, I'm going to have to place my ammeter in this circuit, right? And so I'm actually going to have to break the circuit somewhere. And, you know, I could open the circuit up here, place my meter, you know, from negative to positive, but I've got to put my meter in line in the circuit. And we're using that same principle that current is common in a series circuit. So we don't want to create another path for current to flow. We want the current to flow through this meter and also flow through R1, R2, and R3, right? And so basically what I have to do is I have to break the circuit. I'm going to have to disconnect the circuit somewhere so that I can put in an ammeter to take that measurement. And we're going to see voltage, how we do that, and it's a little bit easier. And we'll see some devices. We'll talk about some ammeters that we can take that measurement a little bit easier. But if I've got a typical multimeter, I'm going to have to break the circuit so the current will flow through the meter. And that's really why, one of the reasons why we use voltage more in troubleshooting than we do current, at least to start with. Any questions about how we got 1 amp or 6 ohms? All right. Now, taking it a step further, looking at the current through R1, R2, and R3, what they're showing you here is that it's 1 amp, right? We know that current's common in a series circuit. So I've got 1 amp here, 1 amp here, 1 amp here, just like we talked about with that ammeter. No matter where I'm taking the measurement from, I'm going to get 1 amp in this circuit. Now, we can also measure or calculate the voltage drop across each one of these resistors, right? And you remember when we were talking about resistors, we said that the two purposes for a resistor, one was to limit current, right? Because it provides an opposition to current flow, so limit current. The other was
develop voltage.
Develop voltage, exactly. Develop voltage. You also may hear it said as drop voltage. You know, you'll hear me say that a lot. I'll use that term, drop voltage, develop voltage, exactly. So we've got this amp of current that's running through each one of these resistors. And as this amp of current goes through, I can use Ohm's law again, but now I'm going to use Ohm's law with the individual values of R1 versus those totals. And I can calculate the voltage drop. Remember, Ohm's law said that voltage is equal to current times resistance. My current is 1 amp through the entire circuit. So I've got 1 amp through R1. My resistance at R1 is 1 ohm. So multiply 1 times 1, I get 1 volt, right? So I get 1 volt that is developed or that is dropped across R1. Right? You can see that formula worked out here. Voltage across R1 is the current through R1 times the resistance. I'm going to get 1 volt. Now, we use the same 1 amp of current that's moving through R2. Now we've got increased in resistors. We've got 2 ohm resistors. So this resistor is twice as big as the R1. Use the same formula. Voltage is equal to current times resistance. My current of 1 amp times my resistance of 2 ohms now gives me my 2 volts across R2, right? So I've got 1 volt that's developed across R1. I've got 1 volt that's developed across R2. Same formula, 1 amp times 3 ohms. I got 3 volts that is developed across R3. Does that make sense? So 1, 2, 3 ohms, 1, 2, and 3 volts, all because we got that 1 amp of current that's moving through this entire circuit. Now, we mentioned before, when you take the TKT, they've got to make sure that the math is simple. I don't know that it will be this simple. I mean, this is, you know, this 1 times 1 stuff is pretty easy. It might get a little bit more complex than that. However, the concept remains the same. I'm going to take my current, multiply by my resistance, and I get the voltage drop across that resistor. Same thing with R2 and same thing with R3. Now, a couple different things that we can notice. One, it says, notice that the resistor, the largest resistor, drops the most voltage, develops the most voltage. You know, this 3 ohm resistor develops 3 volts. So it is a much larger voltage drop. Yep, voltage drop. And then also notice that we can hold up 1 second. Also notice that we can look at Kirchhoff's voltage law. And remember, we talked about Kirchhoff, and Kirchhoff said that you know, the algebraic sum of the voltages in a closed loop equals 0. Kirchhoff also said it in a way that the applied voltage is equal to the sum of the voltage drops. However you want to phrase it, basically what he is telling you is that the amount of voltage that is applied is going to equal all of the voltage drops, right? And so if we've got 6 volts that was applied, that developed a current of 1 amp, and we wind up with 1 volt, 2 volts, and 3 volts, which for a total is 6 volts. You know, 6 volts equals 6 volts, right? That's what we have right here. Voltage applied, we add those voltage drops up, 1, 2, and 3, we get 6 volts. That's what Kirchhoff was saying, is that your voltage applied is going to equal your voltage drops across those resistors. There's no mysterious 3 volts somewhere, or there's no voltage that's being stored somewhere in this, you know, completely resistive circuit. Any questions about that?
We're gonna start doing more like our own kind of thing, so we can figure it out later.
Yes, yes, yeah. We're gonna get a chance for you guys to work a few problems so that we can make sure that we got it. Absolutely.
Okay, cool.
Yep. Okay. Now, same circuit, right? Very simple series DC resistive circuit. You know, DC direct current. It's, you know, voltage is applied, and I got current that's moving clockwise. It continues, doesn't stop. And then I've got only resistors. That's why it's that resistive circuit. We went through how to calculate the totals. We had a total voltage that was given. We calculated our total resistance by adding up our 3 resistors, gave us our total current, which is also our current throughout the entire circuit. We then calculated our voltage drops across R1, R2, and R3. The next step is we can look at power, right? We said power is equal to current times voltage. I told you we do a pretty good job of keeping you on your toes and mixing these together. You can see we've power is equal to I times E, and then we use V in the very next line. And so you're going to see E and V, a lot of different you know, representations of voltage. Just know that when you see E or you see V, we're talking about voltage. And so here we have totals. If we're going to calculate the totals, we always use the total or the applied, right? The total current, the applied voltage, right? So we're looking at power total. So I'm going to take my total current, which was 1 amp, right? Current's common in a series circuit, so we don't have to worry about getting confused there, because total current is the same throughout the circuit. And we're going to take our applied voltage, which was 6 volts. Our 1 amp times 6 volts gives us 6 watts, right? 6 watts. That's our power. Total power for this circuit is 6 watts. Now, we can also do the same thing using the same power formula. We can do that with R1, R2, and R3. I can use my current through R1, my voltage drop across R1, and calculate my power. Power is equal to current times voltage. You know, for R1, it was 1 amp and 1 volt. So that means I've got 1 watt through R1, 1 watt of power. Now, remember, we said that power, when we're talking about especially these resistors, we're saying that that power is going to be dissipated as heat, right? And so, you know, we got to make sure that if we are expecting 1 watt of power, well, is our component rated higher than 1 watt? Is it large enough? And this is one of the few times where you actually can look at a component and the physical size actually is a good indication of you know, its ability to dissipate heat. And so therefore, you know, if you see these resistors and they're all series circuit, and we've got, you know, one that's much smaller than the others, well, that could be an issue because it may not dissipate as much heat. And you're going to see that just as we saw before with our voltage, we've got power that's going to be used by each one of these resistors, 1 watt. R2, once again, 1 amp of current, 2 volts, so therefore 2 watts. And R3, 1 amp of current, series circuit, current's always the same. 3 volts is what we calculated before, so that's 3 watts. Notice that your wattage, your power, we said we had a total of 6 watts. I had 1, 2, and 3. I add those together. My current, or I'm sorry, my power, my wattage should equal, you know, the total power applied should equal, you know, what I have dissipated by my resistors. Here we have a series circuit, and this is, you know, going back to a little bit of what we talked about in terms of batteries and having supplies that are either series aiding or series opposing. You know, if you are given multiple power supplies, DC power supplies in a circuit, what you want to do is really just take a look at those circuits and see which way take a look at those DC supplies and see which way they are forcing current to flow, right? And we're going to talk about electrons, so we're talking about negative to positive. So if I look at this 6-volt supply, it's pushing electrons clockwise. If I look at this 3-volt supply, you know, they're going to be repelled from this negative side, attracted toward this positive side, and so it's also pushing clockwise. Here, 8-volt, clockwise. This 5-volt, clockwise. 10-volt, you can see they're all pushing in electrons in the same direction. And so these are truly series aiding supplies. You know, these are series aiding DC supplies, batteries. They're put in the circuit and they're all pushing electrons in the same way, in the same direction. And so therefore, if I wanted to find out the equivalent DC source, it's just a matter of adding all of these together. You know, I take 6 volts, 3 volts, 8 volts, 5 volts, 10 volts, add them all together, and you can see you get a total of 32 volts. That's all because they're pushing electrons in this clockwise, and it's not so much clockwise or counterclockwise that makes the difference. It's the fact that they're all pushing in the same direction, right? Since they're all pushing clockwise here, that means that we add them all together, and it's the same as having a source, a DC source of 32 volts. Now you can see here, this, once again, series circuit. There's only one path for current to flow. I've got voltage source 1 that's pushing clockwise, you know, negative. So those electrons repelled from the negative side of this battery. So it's pushing clockwise. But then notice VS2. I've got a 3-volt battery here that's pushing electrons in the opposite direction. You see that? They're pushing electrons counterclockwise. Uh-oh, hold on a second. I accidentally hit that. Okay. So this VS1 is pushing clockwise, VS2 counterclockwise. VS3, repelled from the negative side, is pushing electrons clockwise. VS4, counterclockwise. And then VS5, once again, pushing clockwise. And so if this was the case, so now you have series opposing supplies, you would add up, those that are in the same directions. And so VS1, VS3, and VS5, you'd add all those together. So it looks like 18, 24. And then you would subtract those that are pushing in the opposite direction, those that are opposing that supply. And so that looks like VS2 and VS4, which is another 8 volts. So you wind up with a total of 16 volts. And really, this is the same supplies. It's just now you've taken the supplies, instead of them all being series aiding, you've got 2 that are series opposing.
But why would you do that?
Yeah, great question. Why would you do that?
Is it just theoretical math, or is there an actual use to do that?
A lot of this, because there's a different way. If I wanted to, let's say I think we started off with 32 volts. And if I wanted to get that 32 volts down to something other than 32 to 16 or 24, whatever it may have been, there's another way to do that other than using series opposing supplies. And so I would say, don't quote me on this and say that there's never a use for series opposing supplies. I'm sure there is, but in the most case, we're going to do this. If I've got a supply that's 32 volts and I really want to drop it to 16, we're going to see here in a minute voltage dividers where we can do that. And I can use resistors to limit the current versus having a much more expensive supply in place that's having to oppose. So I would say for most of us, especially at this exercise, this is more theoretical, right? So notice that what series aiding looks like, they're all pushing in the same direction, which is what we're going to have most of the time, especially when we're dealing with batteries. And we know, like those 1.5 volt cells, we're going to have multiple batteries. And then realize that if I have batteries that are opposing, pushing in the opposite direction, they're actually, not aiding, but going against the original voltage that you had. So I'd say right now, especially for us, it's more theoretical than anything. All right, so we're going to call this a voltage divider network. All right, we have a series circuit. Now, when I say series circuit, you may say, wait a second. I see multiple paths for current to flow. Electrons are forced this counterclockwise direction, and they get to this point, and I have a point here, so some could go up and some could go out. Well, the only thing is there's no complete path for current to flow out here, right? I mean, you can see that there's these test points, if you will, these tabs that we can take advantage of later. But right now, I could completely remove these and it doesn't change the circuit because there's just nothing out here for electrons to flow through.
Is it just a dead end?
Yeah, it's a dead end. It's a dead end. It's an open. We're going to take advantage of this at some point. We can actually go out here and put a load out here. But right now, what we're talking about, and to be able to walk through this process, we're really still talking about series circuits. Don't let these extra tabs out here, these dead ends, if you will, don't let them confuse you, because electrons are not going to run out to this dead end, and stop. these electrons are looking for that complete path. And so they're going to continue on and go all the way through this circuit, go up through R2 and up through R1. Now we call this a voltage divider network, a voltage divider circuit, because what it's going to do is it's going to take my original voltage, and it's nothing more than 2 series resistors, but it's going to take my original voltage and it's going to divide it for me, right? And so we already know that with 12 volts, I can calculate, my total current, my total resistance. I can do all the calculations. So let's just step through that and let's just see what we get. And then we'll walk back and we'll kind of, draw some conclusions that we could have made early on. So our total, I'm going to calculate my total resistance. I've got 2 resistors that are in series. All I have to do is add them together, right? These absolutely 2 kilo ohms, right? This current, all of it's going to flow through R2 and through R1. And so it's a matter of adding those 2 together. That's the total resistance that will be felt by this circuit. So I take 1K ohm, which is 1,000 and 1,000, and I get 2 K ohms, right? Remember, K is times 10 to the third, or 1,000, right? So I got 2 kilo ohms. That's my total resistance. Now that I have total resistance, I can use Ohm's law and calculate what my current is in the circuit. It's a series circuit, so this is going to be the total current, but this is also going to be the current that's going to flow through R2 and R1. So I take my 12 volts, which is my applied voltage. I divide it by my total resistance, which we said was 2 kilo ohms. And I get 12 volts divided by 2 kilo ohms, or 6 milliamps. Now remember, when we were doing the math section and we're going through some of this math and working with engineering notation, we said that there's a couple different ways you can do the math, right? You could go ahead and convert this if you wanted to and say that I'm going to take 12 and I'm going to divide that by 2,000. And if I did that, I would get, 0.006 or 6 milliamps. Now, the other thing we said we could do is we also could take and do the math, right? Do the division, but subtract the exponents since we're dividing. In other words, I could take my 12 volts. 12 is the same as 12 times 10 to the 0. I've got 2 times 10 to the third. I just do the math first. 12 divided by 2 gives me my 6. And then I just subtract the exponent. So I had a 0 for my voltage, times 10 to the 0. And I had times 10 to the third. So I subtract that 3 from 0, and I get a -3. So I wind up with a -3, which -3 times 10 to the -3 is milli, right? So I get 6 milliamps. Either one of those ways is fine. If you want to convert it and then do it so that you come up with a very small number and then move that back to 6 milliamps, or if you feel comfortable working with kilo, knowing that when I divide a number by kilo, it's going to move me to milli, right? 2 kilo ohms, 6 milliamps. So I've got 6 milliamps. That's my current. My total current that's flowing in this circuit is 6 milliamps throughout the entire circuit. Anywhere I measure in this circuit, I've got 6 milliamps. Now, from there, we said that we could measure or we could calculate our voltage, right? We know that the voltage through or the current through R2 and R1 is 6 milliamps. I can use Ohm's law. Voltage is equal to current times resistance. 6 milliamps times my 1 kilo ohm. That's going to give me my voltage drop. And notice that I'm multiplying now milli and kilo. So one number is times 10 to the -3rd. One number is times 10 to the third. We know you multiply those two, they cancel out. And so therefore, I'm going to wind up with 6 volts. 6 milliamps times 1K gives me 6 volts. Here, current 6 milliamps times resistance 1K, I get 6 volts. Now, voltage divider. What's the voltage across R2? How much voltage was developed across R2? Right? We said voltage is equal to 6 milliamps times 1K. We got how much voltage? 6 volts, right? 6 volts. 6 volts. Absolutely. 6 volts. How many did we get across R1?
Also 6.
Also 6. Yeah, also 6 volts. Look at the value of R1 and R2. They're equal. And you start thinking about the math. Well, that makes perfect sense because the current that is flowing through both of those is the same current. Well, if I've got the same resistance, then I must have the same voltage dropped across each one, 6 volts and 6 volts. And you can see why they call this a voltage divider, because I'm starting out with 12 volts. But if I have 2 resistors in series, those resistors are each going to drop or develop a portion of the voltage. And they're going to drop voltage based on their value in comparison with one another. If they're equal resistors, then the voltage drop is going to be equal, right? For example, let's say that this was not a 1K ohm resistor. Let's say that both of these were 10K resistors. If they're both 10K resistors, what's the voltage drop going to be across R2?
6.
6. Absolutely, 6. Now, how is that possible? How is that possible that my voltage drop is still 6, but I changed the value of my resistor? Something's got to change, right? If I change the value of my resistor, what else is going to change?
Voltage.
Okay, so my voltage stayed at 6, right? My voltage stayed at 6 across R1, and my voltage stayed at 6 across R2 because these two resistors are equal. But my total resistance, you can see, if I move this to 10, if I add them just like I normally would to calculate my total resistance, 10K and 10K, that gives me a total of 20K. So what happens to my current when I increase my resistance like that?
Goes up.
So think about it. We said resistors, they develop voltage and they also oppose current flow, right? So if I put more opposition in the circuit, do you think current goes up or goes down?
Current goes down because it's harder to capacitor.
It goes down. It goes down. Absolutely. You know, think of it this way. If there is more resistance to you, more cars on the road as you're driving to work, does your driving time go up or go down? You know, it's going to take you longer to get there, right? You're going to have less current in traffic. You know, it's going to be slower. And so what I'm getting at is we can take a look at this circuit, this voltage divider, and without going through all the calculations, if we can just look at the resistance comparing R1 and R2, we can get an idea of what this voltage might look like, right? So if on the test, they gave you a voltage divider circuit and they ask you, what is the voltage here? If you see that R1 and R2 are equal, that means half the voltage is going to be this resistor, half the voltage that resistor. It becomes as simple at that point is saying, okay, half of my voltage, 12 volts. Well, that means that this is going to be 6. Now, am I saying that you're wrong if you go through and you calculate total resistance and you calculate total current, and then you come back and you calculate the voltage drop across? No, that's not wrong. I mean, that's the right way to do it. And it's always a great check. But what I'm saying is that if you're under a time pressure, like we've talked a little bit in terms of this test, and we've heard some folks say that that's really one of the biggest challenges is the time. You know, you need to find ways where you can get to the answer quicker. And so if you see, oh, voltage divider, equal resistors, okay, half voltage here, half voltage there. You know, if you had a voltage divider, and let's say that this was 1K and this was 10K, so this one is 10 times as large as this one, then the voltage drop across this resistor should be 10 times as much as this one. So looking at the relationship between these two resistors can allow you to answer. And we'll see some of those questions. I think they may be at the end of this presentation. I know they're in the class presentation. And so we'll get a chance to kind of test out some of those. I hate to even use the word shortcut, but a quick way to the right answer. All right. Okay, so here we have, let's just, I wish I could shield a lot of this. Let's just take a quick gander, all right? Tell me about the voltage drop across R2 versus R1. Which one's gonna have the highest voltage drop, R1 or R2?
R2,
R2 will, why?
because it's double the ohms.
It's double the ohms, which means it's gonna develop double the voltage, right? Absolutely. If I would say that this is 2 parts, this is 1 part, you know, I could divide this number by 3. That gives me 2 volts. So 2 volts here, 4 volts there. That's where we're going to wind up. Before we do any of the math, we already know that this is going to be twice as large. Absolutely. And so if we take a look at this circuit, 6 volts applied, I've got a 2 ohm resistor and a 4 ohm resistor. I go through and I can calculate everything here. You know, voltage. Let's see, R total is the total resistance equal to 6 ohms, right? So that's what they're saying is we go ahead and add those 6 ohms. We know that voltage R1 is going to be 2 volts. Voltage R2 is going to be 4 volts. You know, they're jumping to, hey, I know real quick that we're looking at twice as much voltage here. And the only way R2 could be twice as much is if it's 4 and 2 with 6 volts. And then they're going through and using the math to validate it, to ensure that that's right. You know, R total, R1 plus R2 is going to give me 6 ohms. My current total, I'm going to take my 6 volts, divide it by my 6 ohms, get that 1 amp again. Like I said, we're keeping the math really, really, really simple here. And then I'm going to go and use that same current, that 1 amp, volts R1, 1 amp plus 1 amp times 2 ohms is going to give me 2 volts. 1 amp times 4 ohm is going to give me 4 volts. And there we have it. You know, 4 volts and 2 volts. All right. So once again, looking at what we've kind of talked about in terms of voltage divider, going back and taking a look at the first circuit that we had, where we calculated our R total being 6 ohms, R1 plus R2 plus R3. Once again, we've already done these calculations. Our voltages was 1 volt, 2 volts, and 3 volts. now it should be real easy to see with that same current and looking at the relationship between these resistors, and the larger the resistor, the greater the voltage drop, and it's proportional. So, the voltage across R2 has got to be twice as large as the voltage across R1. Was it? Yes. 1 volt across R 1 volt across R1 and 2 volts across R2. Same thing with R3 and R1. 3 volts and 1 volt. Then we can also look at our Kirchhoff's voltage law, our applied voltage, looking at the voltage drops. Remember, the applied voltage is equal to the sum of the voltage drops, 6 volts, 1, 2, and 3, 6 volts. So everything remains the same. I mean, it's a series circuit. Everything holds true. But, you can quickly, looking at the relationship between these resistors, begin to better understand and anticipate what you're going to get across these different resistors. You'll see some questions in the practice test where some of the answers are impossible. Just looking at the relationship and being able to know a larger resistor is going to develop more voltage. And we'll see some of the same things when we get into parallel, some of the very, very quick things that you can understand as you look at a circuit. I mean, some things that you immediately can take away. One of the things it's saying here is this concept of where you're looking at this total and the total voltage and quickly getting to that amount. Obviously, if things don't divide equally, it becomes much more difficult to just make that assumption, right? If you're dealing with something that is a fractional amount, it becomes much more difficult to figure out. All right, so let's see. So we've got 12 volts, right? Same circuit. All we've done is we've increased the voltage. By increasing the voltage, we're going to take a look at our voltage drops across R1, R2, and R3, right? We gotta, we want to make sure that everything remains the same in terms of our process to calculate what our total resistance is going to be, what our current's going to be. I mean, all of that remains the same. Kirchhoff's law is still going to hold true. Everything's going to be the same. The only difference is, since we kind of know this process, instead of going through all of that at the beginning, we can just take a look and say, okay, well, I got 12 volts and I've got, R total, I'm looking at 6. So I know that my voltage to resistance is 2 to 1, right? For every 2 volts, I've got 1 ohm. And so therefore I can just multiply these by 2, right? So I get 2, 4, and 6, right? 2 volts, 4 volts, and 6 volts are my voltage drops, or my expected voltage drops across each one of these resistors, R1, R2, and R3, right? All we did is say, hey, if my voltage that's going to be developed over these resistors, and it's the greater the resistance, the greater the voltage going to be developed. Let me just look at the ratio between these two. Before it was 6 to 6, and so 1 to 1, 1 ohm equal 1 volt. Here it's 12, so it's 2 to 1. So it's really easy to say, okay, well, that means that I've got 2 volts, 4 volts, 6 volts. I can quickly figure that out. I can still go through, and if I did it the old way, and so I'm looking at 6 ohms, my 12 volts, I'm going to divide that by 6 ohms, gives me 2 amps. 2 amps multiplied across each, you're going to see it's still 2 volts, 4 volts, and 6 volts. Kirchhoff's voltage law, does it hold true? 12 volts, 2, 4, and 6, which is 12 volts. Yes, it holds true. Remember, Kirchhoff said that the sum of the voltage applied must equal the voltage drops, right? So therefore 12 is equal to 12. And then we can also calculate our powers. We can go in and we can calculate the power for each resistor, our power total. The power total would be 12 volts by 2 amps, which was 24 watts. Should be 24 watts here somewhere. Yep, 24 watts is the total. Now, also notice that one of the things they did here is instead of using the power formula on each R1, R2, and R3, they're using what you have, right? They're using the voltage drop of 2 volts across R1, and they're using the value of R1, which was 1 ohm. And you may remember that one of the power formulas was E squared, voltage squared divided by resistance. So we took 2 squared, it'd be 4, divided by 1, to give you 4 watts. And so that works out. Now, I will say that I have found that some folks, they don't feel 100% comfortable going to that formula for the beginning. And I mentioned that you can still calculate everything you need with power is equal to current times resistance. The only difference is you would have to calculate your current, which is not a big deal because it's 2 volts, it's 1 ohm, voltage divided by resistance gives me that current of 2 amps. So now I have my current, I have my voltage, 2 amps, 2 volts, and so I get my wattage across R1 at 4 watts. And so you can still do it. You can, it takes one more step. You have to calculate current instead of going through this voltage squared divided by resistance, but it's still easy to get there. And that same 2 amps flows through all of these. And so remember, this was 4 volts. 2 amps and 4 volts is going to give me 8 watts. 2 amps and 6 volts is going to give me 12 watts. My totals 12 volts and 2 amps is 24 watts, or I could just add up my wattage, 6 or 12, 8, and 4 for also 24. Questions about that circuit? Okay. We'll move. There we go. So now we're going to make another change. Same circuit. Only thing we've done is we have changed the voltage. Remember, we started off with 6 volts, then we turned it up to 12 volts, and now we've backed it down to 3 volts. Right, so 3 volts. We go through that same process. Well, we were looking at our resistance and comparing it to the applied voltage. And when it was 6 and 6, we said that was a 1-to-1 ratio. And so therefore the voltage drops would just be, basically our resistor values, right? Here, what we have is a 1/2-to-1. And so therefore, when we're looking at our voltage drops, it's going to be half of the resistive value of each one of these. Keep in mind, this little trick that we're using, in essence, what we're doing is we're using, this voltage and resistance. We're basically calculating the current. And so if you think about 3 volts and my total current or total resistance was 6 ohms, right? Voltage divided by resistance is going to give me, a 1/2, or 0.5, or 500 milliamps would be my circuit current, 500 milliamps. And then if I went in and I start multiplying by my resistance, it's going to be these same values. 0.5 volts. It's going to be 1 volt. It's going to be 1.5 volts. I've got a current of 500 milliamps. And so in many ways, we're doing the same thing. We're just doing it in a way that's comfortable for us to be able to look at the voltage divider, the total resistance, and see, does it divide equally into my applied voltage? Once again, if it doesn't divide, if it's, if this was like 1.374, well, then it becomes more complicated. It's probably easier just to go ahead and do all the math. If it divides equally, it becomes, real simple to figure out what the voltage drop would be across each one of these resistors. Kirchhoff's law still holds true. 3 volts, 0.5.
Where does it tell us that it's?
What's that?
Where does it tell us that it's half though?
Okay, so where do we get the half? And really what we're looking at is we're looking at this ratio, right?
Yeah,
so,
where does that ratio come from though? Is there math to give?
So all they're doing, looking at that ratio, is my resistors. So I have 6 ohms, right? And then look at my applied voltage.
6 divided.
All right then.
And so for,
That makes sense.
There you go. There you go. That's all we're doing. And so like before, when we had 6 ohms and 6 volts, well, it was just, 1 volt, 2 volts, 3 volts. And then we had same resistors, 6 ohms, and we had 12 volts. Well, 12 volts means that it's 2 to 1, right? 2 volts for every ohm. That was the ratio. And so then it was 2 volts, 4 volts, 6 volts, right? So that's all they're doing, is they're taking a quick look at my resistors, 1, 2, and 3. Okay, what's that? That's 6. Now, is this a multiple of are they multiples of each other?
Yeah.
If like, for example, if this was 2 volts, then we could say it was
1/3.
1/3, right? Exactly.
Yeah, no, I felt dumb as soon as you explained it.
No, don't feel dumb, not at all. All right, so Kirchhoff's law, all that still holds true. We're in great shape. And it's going to tell you again, a reminder here, remember, this is really when they can be divided equally. Otherwise, do the math. The math will always work. If this is some number and you're trying to figure out, okay, what would the ratio be? And if it takes you more than a split second, then it's obvious it's not dividing. It's not going to be divisible equally. Just move on and do the math, right? Calculate total resistance, just my voltage, use Ohm's law, voltage divided by resistance gives me my current. Same current throughout the circuit. Go ahead and start multiplying current and get your voltage drops, right? So it won't take you that much longer. If you spend more than a second, I would say looking at that and wondering if you could take a shortcut, then go ahead and do the math. All right, so we took a look at series resistive circuits. We looked at the Ohm's law. We've utilized Ohm's law to make some calculations. We verified that with Kirchhoff's. We looked at power to make sure that we could calculate the power. And so now let's take a few minutes and see if we can calculate all of these different, from R total all the way to the power dissipated across each resistor. Let's see if we can do that. So let's take about, about 5 minutes and see if we can do that. All right. So go ahead and grab you a sheet of paper and a pencil and see if we can work that out right quick. All right, what do you guys think? What'd you get for resistance total?
20.
It's 20, right? Series circuit. In series circuit, all we have to do is add the resistors up 2, 6, and 12. We get that total resistance of 20 ohms. Oh man, you didn't see that. Current total. One amp. We're keeping that math simple. That's right, 1 amp. We took our 20 volts, divided it by our 20 ohms to give us 1 amp. The next three are really tough. Current through R1, R2, and R3. What is that? 1, right? Series circuit. Just because they put it up there, don't mean we've got to calculate anything. All right, still 1 amp. The voltage across R1. 2, right? Voltage is equal to current times resistance. 1 amp is my current, 2 ohms is my resistance, 2 volts. How about R2? 6 volts. R3? 12 volts. All right. How about power total? Said the power is equal to current times voltage. Talking about our power total here. 20. Okay. We took our 20 volts, multiplied that by our current total of 1 amp. So we get 20, and it's 20 what?
Watts.
Yes, there's a joke in there somewhere. Yes. 20 watts. Yes. Yeah. 20 watts.
Yes.
Yes. Who's on first? And then power across R1. Our voltage drop times our current.
18.
Okay. So what was the voltage drop across R1?
2.
2 volts. And then what was our current through R1? 1. Okay. So our formula would be power is equal to current times voltage, or 1 amp times 2 volts. So 1 times 2 would be 2 watts, right? Power in R2, 1 amp.
6 watts.
6 volts. So that was 6 watts. Absolutely. And then R3?
12 watts.
12 watts. Absolutely. Absolutely. So you can see the answers there. Very good. Just a couple questions to kind of go back and capture some of the discussion. How many paths for current flow in a series circuit?
1.
1 path, right? That's 1 path. That's what makes it a series circuit. There's only 1 path for current flow, and that's why we can say that current is common, because it's the same current that's flowing in that 1 path throughout the entire circuit. And I just answered what was the second question there. What is common in a series circuit? Current. Absolutely. Current is. Resistors connected in series are referred to as
Series circuit.
it is a series circuit. It is a series circuit. So let's take a look at this schematic, right? And we've got R1 and R2 in a series circuit. And then we had these taps here, and we were talking about how the relationship between R1 and R2, how it impacted. What do we call this circuit? Do you remember? We said it would take our original voltage and do what to it?
Divider.
Voltage divider. Absolutely. Yeah. So you may hear this series circuit referred to as a voltage divider. A voltage divider. And then how do you calculate resistance total for series resistors?
Altogether.
We just add them up, right? All we have to do is add, however many we have, 1, 2, 3, 4, 5, to, whatever number. We just add them up. If they're all in series, those those electrons are going to have to flow through all of those resistors, and so we just add them up. What are the voltage drops for R1 and R2 in this voltage divider network?
Is it 3 and 7?
Is it 3 and 7? I don't know. Is it 3 and 7? What do you guys think?
Yeah.
You like 3 and 7?
Yep.
All right. So how did you get 3 and 7 so quick?
The 10 divided by 20.
Okay. Yeah. So you said that basically the ratio is 1 volt for
It's
2
the
ohms?
half that you just set up on one of the other problems. So yeah, and
Absolutely.
divided 6 by 2 and
That's right.
14 by 2.
That's right. And you can do a quick, if you go 3 and 7, okay, well that ratio holds true here. Well, does that equal 10? 3 and 7? Yeah. So it works. Good job. Questions about series resistive circuits?
No.
No. Okay. Let's see what time we got. About 15 after. Not quite as easy to get to some of these resources. So let me share this. We'll watch this right quick and we'll probably be ready for a break. Let's see. Not sure how long this is.
Our favorite batteries and resistors. We can start to assemble these into some circuits. And here's a circuit shown here. It has a battery and it has 3 resistors in a configuration that's called a series resistor configuration. Series resistors is a familiar pattern, and what you're looking for is resistors that are connected head to tail to head to tail. So these 3 resistors are in series because their succession of nodes are all connected one after the other. So that's that's the pattern that tells you this is a series resistor connection. So we're going to label these our resistors here. We'll call this R1, R2, and R3. And we'll label this as V. And the unknown in this is what is the current that's flowing here. That's what we want to know. We know V, we want to know I. Now, the one thing we know about I is I flows down into the resistor R1. All of the current comes out of the other end of resistor R1 because it has to. It can't pile up inside there. All of that goes into here. and all that comes out of R3, and I returns to the place it came from, which is the battery. So that's a characteristic of series resistors, is in a series configuration, is they are head to tail. And that means that all the components, all the resistors, share the same current. That's the key thing. The thing that we don't know that's different between each resistors is the voltage here and the voltage here. Let's call that V1. This is V2 plus minus, and this is V3 plus minus. So in general, if these resistors are different values, because they have the same current going through them, Ohm's law tells us these voltages will all be different. So the question I want to answer with series resistors is, could I replace all three of these with a single resistor that caused the same current to flow? That's the question we have on the table right now. So we make some observations. We have Ohm's law, our friend Ohm's law. And we know that means V equals I times R for any resistor. That sets the ratio of voltage to current. And there's another thing we know about this, which is that V3 plus V2 plus V1, those are the voltages across each resistor. Those three voltages have to add up to this voltage because of the way the wires are connected. So the main voltage from the battery equals V1 plus V2 plus V3. We know that's for sure. And now what we're going to do is we're going to write Ohm's law for each of these individual resistors. V1 equals I, and I is the same for everybody, times R1. V2, this voltage here, equals I times R2. And V3 equals I times R3. Now you can see if I had 4 or 5 or 6 resistors, I would have 4 or 5 or 6 equations just like this for each resistor that was in series. So now what I'm going to do is substitute these voltages into here, and then we'll make an observation. So let's do that substitution. I can say V equals I R1 plus I R2 plus I R3. And because it's the same I on every resistor, I can write V equals I. I'm going to factor out the I. R1 plus R2 plus R3. Now what I want to do is take a moment here and compare this expression to this one here, the original Ohm's law. Right? There's Ohm's law. So we have V equals I, some current, times some resistor. I can come up with a resistor value, a single resistor, that would give me the same Ohm's law. And that is going to be called, let's draw it over here. Here's our battery. And I'm going to say there's a resistor that I can draw here, R series, that's equivalent to the 3 resistors here. And it's equivalent in the sense that it makes I flow here. That's what we mean by equivalent. So in our case, to get the same current to flow there, I would say V equals I times R series. In which case, what I've done is I've said that R series is what? Is the sum of these 3 things. R1 plus R2 plus R3. This is how we think about series resistors. We can replace a set of series resistors with a single resistor that's equivalent to it if we add the resistors up. Let's just do a really fast example to see how this works. I'm going to move the screen. Here's an example with three resistors. I've labeled them 100 ohms, 50 ohms, and 150 ohms. And what I want to know is the current here. And we'll put in a voltage. Let's say it's 1.5 volts. Just a single small battery. So what is the equivalent resistance here? One way to figure this out and to simplify the circuit is to replace all three of those resistors with a series resistor, Rs. And that is, as we said here, it's the sum, so it's 100 plus 50 plus 150. And that adds up to 300 ohms. So that's the value of the equivalent series resistor right here. And if I want to calculate the current, I equals V over R. In this case, it's R series. And that equals 1.5 divided by 300. And if I do my calculations right, that comes out to 0.005 amperes, or an easier way to say it is 5 milliamperes. So that's I. And now that I know I can go ahead and I can calculate the voltage at each point across each resistor. Because I know I know R, I can calculate V. So V1, which is the voltage across that resistor, V1 equals I, R1, as we said before. So it's 5 milliamps times 100 ohms, 0.5 volts. Let's do it for the other one. V2 equals I, same I, this time times R2, 5 milliamps times 50 ohms, and that equals 0.25 volts. And finally, we do V3. This is plus minus V3, and that equals the same current again, times 150 ohms, which is equal to 0.75 volts. So we've solved the voltage and the current on every resistor. So this circuit is completely solved. And let's do one final check. Let's add this up. 5 is 0. Carry the 1, 6, 7, 8, 15, 1.5 volts, and that's very handy because that is the same as that. So indeed, the voltages across the resistors did add up to the full battery that was applied. There's one more thing I want to point out. Here's an example of some series resistors. And that's a familiar pattern, and you'll say, oh, those are series resistors. Now, be careful, because if there's a wire here going off and there's doing this, or there's a wire here connected to this node here, this still looks like they're in series, but there might be current flowing in these branches here. If there's current flowing out anywhere along a series branch, anywhere along what looks like a series branch, then this I may or may not be the same as this eye, and it might not be the same as this. So you got to be careful here. If you see branches going off your series resistors, these are not in series unless these are zero current. If that's zero current, and if that is zero current, then you can consider these in series. So that's just something to be careful of when you are looking at a circuit and you see things that look like they're in series, but they have little branches coming off. So a little warning there. So that's our series resistors. If you have resistors in series, you add them up to get an equivalent resistance. Now that we have our collection of components, our favorite batteries and resistors, we can start to assemble these into some.
Stop. All right. So, did we mention two things that he said? First of all, you notice that what he did is he had his 3 resistors in series, and there's nothing magical once again about 3 resistors. It could be, any number of resistors. Let's not, get so caught up on just 3. But what he did is he took his 3 resistors and then he talked about the possibility of combining those into one large resistor using the value. He totaled them together and came up with whatever that resistance was. That's the same thing that we've been doing in terms of taking those 3 resistors and calculating our resistance total. I do want to mention what he said about the possibility of thinking about that as one resistor. When we get into some more complex circuits and we have to start simplifying some circuits, there will be some times when we will actually redraw some circuits. This is not something that you're going to do when you're sitting down to troubleshoot a schematic. You're not going to start redrawing the circuit. But when we're doing some of our calculations, when we're working through everything, there are times we'll actually take a series parallel circuit and start combining different resistors, whether they be in series or in parallel. And so we may take 3 series resistors and then redraw the circuit as that's one resistor, just so it's a little bit more simplified for us to work through some of those calculations further down the line. And so, that's a good point to pick up right now, even though we don't have to do it yet. The other thing is, I don't know if anybody picked up on it or not, but he kept putting, when he's talking about current flow, he put an arrow up there and he was, showing current flowing positive to negative, right? You're going to see that, some people are some just not really concerned about the direction. They're just showing current flow. Some are talking about a different type of current flow in terms of conventional versus electron. Don't get caught up on that. For us, we're talking about electron current flow, so it's always easiest for us to talk about negative to positive. All right, so we're at 9:30. Let's take a 10-minute break and come back at 9:40. All right, see you guys in 10 minutes. Okay, you guys see parallel DC resistive circuits?
Mhm.
All right, so we talked about series, one path for current to flow, current's common through the entire circuit. We're going to change things slightly, but not everything's changing. When I say not everything's changing, Ohm's law still remains the same, power still remains the same, but we're going to look at a little bit different circuit, parallel circuits. now we've got multiple paths for current to flow. And we're going to see that in a schematic in just a second. We're going to talk about how to calculate that total resistance. Remember, in the series circuit, since all the current flowed through that one circuit, the multiple path, since all the current flowed through one path, multiple resistors, we just add those resistors together. What we're going to see now is multiple paths, and so not all of the current will flow through every resistor, right? We'll figure out, we'll talk about how to calculate total resistance. We'll talk about current total and voltage applied, and that Ohm's law remains the same, that relationship between those three variables, but we're going to apply it. We're going to see how it's impacted when we look at a parallel circuit. We're going to do all the calculations, the same calculations that we did before in terms of total voltage and current and resistance, and then voltages across individual resistors and current through individual branches, which is something different for us this time. And so we're gonna calculate all of that out. And then we're also, like we did in series, we're going to take a look at some inferences that we can make and figure out how we might be able to get to an answer of a question even before we do a lot of the calculations. All right, so a parallel circuit. We've got multiple paths for current to flow now, right? Instead of a series circuit where we just had one path for current to flow, now you can see we have these junction points, we'll call them a node, where electrons will get to this point and then have the opportunity to either go through R1 or over through R2. Now we know that resistors oppose current flow. And so the larger the resistor, the larger the opposition to current flow. And so current will always take the path of least resistance, meaning the smallest resistor is going to have the largest amount of current, right? Once again, it's like you in traffic. You hear a traffic report about a lot of traffic in a given area because of a wreck. There's a huge opposition to that traffic, and you're going to find a different way to go. Electrons are going to do the same thing. They're going to see, twice as much current out here at R2, so twice as many electrons are going to go through R1. You're going to take the path of least resistance. This is walking you through the fact that we have, this supply electrons that are moving through this and either go through R1 or R2. Now we say here that voltage is common in a parallel circuit. Current is common in a series circuit. Voltage is common in a parallel circuit. If I'm measuring across R1, so if I had a meter and I place, my black lead at the top of R1 and my red lead at the bottom, I'm in essence measuring here and here. We're saying that this wire has very little resistance, and so it's really the same point. And so what happens is this voltage, 20 volts, that's felt across this power supply is also felt across R1. So the voltage drop across R1 is 20 volts. The voltage drop across R2, if I measure across R2, I'm also going to get 20 volts. And it seems like, wait a minute, I'm increasing the amount of voltage. Well, no, because all I'm doing is I'm connecting in parallel across this battery. So it's going to be 20 volts felt here. It's going to be 20 volts felt here. And I could continue to have R3, R4, R5, however many resistors I wanted in parallel. And each one of those would have 20 volts. And remember, volts was potential difference, 20 volts of potential difference between felt across them. Now, what that means is each one of these currents, the branch current, and when they talk about a branch current, that's what they're saying. Each one of these branches are going to have a different current. R1 is going to have twice as much current as R2. Remember, current takes the path of least resistance, and so therefore, 20 and 10, right? And so if I had, my voltage 20 volts, right? And then if I want to use Ohm's law, voltage divided by resistance equals current, right? So I'm going to have 20 volts divided by 1 ohm, or 20 amps, and 20 ohm or 20 volts divided by 2, so 20 and 10. Absolutely, just using Ohm's law, right? I'm just using that relationship between voltage, resistance, and current, that law, and calculating the branch current through R1, the branch current through R2, right? So voltage is common in a parallel circuit. Now, here's a formula that often looks scary. I can tell you that, once again, keeping things simple, right? And it's hard to do the reciprocal of the reciprocal with complicated math in your head. And so this is going to be, I would say, pretty easy to calculate if you get a question on the test that asks about total resistance in a parallel circuit. Now, remember, here's what's happening in that series circuit. When we had all of the current flowing through those 3 resistors, it went through R1, R2, and R3. So we had to add all of those together. Here in a parallel circuit, those electrons are not going through both R1 and R2. They're going through either R1 or R2. And in fact, what happens is the total resistance, and this is counterintuitive, I think, because most of the time when we think about total, we think about something that's larger, but the total resistance, and if you think back to the video where the gentleman was describing when we're solving those 3 series resistors, and we're thinking about what could we replace that as if we had 1 resistor. In series, it's going to be a larger resistor. In parallel, if we have that same thought process, what could I replace R1 and R2 as? Well, since there are 2 paths for current flow, the resistance that is felt by the supply is actually smaller than the smallest branch. So you can see where I've got a resistance of 1 ohm here. When I start using that formula, 1 over R1 plus 1 over R2, I'm going to always get a number. My R total is always going to be smaller than the smallest branch resistance, right? It's going to be smaller than this 1 ohm. If I use that formula 1 over 1, this is going to be 1 over 1. This is going to be 1 over 2, right? So 1.5, the reciprocal of that. If I take 1 and divide it by 1.5, it's going to be smaller than 1, right? And so it will always be smaller than the smallest branch resistance. You will see questions that will ask you, it'll give you multiple resistors in parallel, and then it will ask you, what's the resistance total? And for example, in this scenario, it might be, what is the resistance total? And it says 0.75 ohms, 10 ohms, 12 ohms, or 30 ohms. Well, even without doing the math, you know that it has to be smaller than the smallest resistance. And so therefore it must be 0.75. It can't be anything larger than this 1 ohm resistor. And so we'll see some questions where you can either get caught up in doing a calculation, or you can quickly say, well, I know the answer there. There's only one that it could possibly be. So parallel circuit, multiple paths for current flow, voltage is what's common, and my resistance total is always going to be smaller than the smallest branch resistor, right? Smaller than the smallest branch resistance. That formula, this is the reciprocal of the sum of reciprocals. I'm taking 1 over R1 plus 1 over R2, could be on out to any number of parallel resistors. And once I get that, I take the reciprocal of that, and it's going to give me a number that is going to be smaller than the smallest branch resistance. All right, so here, if we were looking at our total, first of all, once again, we know that my resistance total is going to have to be smaller than 10 ohms, right? 10 ohms, 20 ohms, 30 ohms. It's got to be smaller than the smallest branch resistance. So it's got to be smaller than 10. Now, what does that look like in the formula? Well, I'm going to take the reciprocal of each one of these resistors. So 1 over 10 plus 1 over 20 plus 1 over 30. You can see they're just reducing this to, dividing 1 by 20, which gives me 0.5, dividing 1 by 30, which gives me 0.033, dividing 1 by 10, which gives me 0.1. We add that together, we get 0.1833. Take the reciprocal, which means I'm dividing 1 by that 0.1833, and I get 5.45. Once again, smaller than the smallest, which was 10, 5.545. That's my resistance total. Now, there are a couple.
Go back forward, just I'm writing it down.
Absolutely. You'll go back. Let me go back to that slide.
Yeah, was I mean, you said you're going to show us a different way because I mean we don't have a calculator for the test.
Yes, absolutely.
Okay.
Absolutely. So this would be, this is, this formula will always work, right? It doesn't matter if there's 2 resistors, if there's 10 resistors, it doesn't matter what their values are. The reciprocal of the sum of reciprocals, while it is not the easiest formula to work with, it will always work.
Okay.
Now, if I have a couple different scenarios, if I have 2 resistors in parallel, only 2 resistors in parallel, I can do what's called the product over the sums. And basically product meaning I'm multiplying, over the sums meaning I'm adding the 2 together. And so you can see I'm taking 10 ohms and multiplying that by 20 ohms to get a value here. And then I'm going to take 10 ohms and add that to 20 ohms. So that gives me 200, 10 times 20, 200 over 30. And that would give me 6.67 ohms. All right. Now, once again, we know that our total is always going to be smaller than the smallest branch resistor. And so therefore it had to be smaller than 10. If we do this calculation and we get 15, something's wrong, right? It's got to be smaller than the smallest. So the product over the sums, usually pretty easy to work with because you're going to have some resistors. I mean, even like this, 10 and 20. Okay, that's not too difficult to work with. 200 over 30, and then we can do a little bit of division there. But it only works with 2 resistors in parallel. Right? If I add a 3rd resistor in parallel, I can't multiply out that 3rd resistor and expect it to work. So it only works with 2. Now there is another scenario. If I'm dealing with equal resistors, doesn't matter how many, it could be 3, could be, now the reason we say 3 is because if it's 2, you could still do product over the sum, right? So if you had 2 equal resistors, you could do either product over the sums, or you could do this formula as well. But this will also work with 3, it'll work with 4, 5, 6, 10, 20, 30, as many, as long as the only criteria here is that they must be equal. You see, I've got 3 10 ohm resistors in parallel. If I've got 3 10 ohm resistors, then the best way to think about it is each one of these, it's an equal division. And so all I have to do is take that value, whatever the resistor is. Here it's 10 ohms, right? You can see I've got 10 ohms repeated in each one of these branches. And then I divide it by the number of branches. Here I've got 10 ohms and I divide it by 3 because I've got 3 branches, and I wind up with 3.33 ohms. Once again, it's got to be smaller than 10. That's what we're expecting, right? So there's 2 shortcuts other than the reciprocal of the sum of reciprocals. You can do product over the sums. You've got 2, or you can do, if you've got equal resistors, you can take the value of the resistor and divide it by the number of resistors, number of branches. All right, so let's take a look at this circuit. We've got 3 10 ohm resistors in parallel. So we know that we've got current that's going to go from negative to positive. It's going to go this counterclockwise direction. It's going to get to this node. Some of the current's going to go through R1. Some of it's going to go on to R2. Some of it's going to go on through R3, right? What can you tell me, knowing how this, seeing how even in a series circuit, current and voltage drops, how this value of resistors and how they play out? What can you tell me about the current in each one of these branches? Since I've got equal resistors, what do you expect will happen with the current?
It'll be equal.
It'll be equal. It'll be equal. Absolutely. Absolutely. We said that current is going to take the path of least resistance. Well, if they're all equal, then you're going to have an equal amount of current flowing in each one of those branches. If I have a branch that has much more resistance in it, well, I'm going to see less current there and more current in the branch that has less resistance. Absolutely. So since we've got equal values of resistors, I'm expecting equal branch currents. Now, what do I do here? I can use my shortcut. Remember, I could take, since each one of these are equal, my 10 ohms divided by 3. And we'd already seen on the previous slide that was 3.33 ohms, which meets the criteria of being smaller than this 10 ohm branch resistor. 3.33. Now, once I have that value, I'm right back into calculation mode, right? I've got my total voltage applied, which was 20 volts. I know my total resistance, which is 3.33. And so I can start calculating currents, right? I can calculate my individual currents. I was actually here. 20 volts divided by 3.33 gives me a total of 6 amps, right? That's my 6 amps. It would be what's leaving my power supply. Now, since I know that, also know the voltage across each one of these resistors. Remember, voltage is common in a parallel circuit. So 20 volts, 20 volts, and 20 volts. I can use Ohm's law. Current is equal to voltage divided by resistance. 20 volts divided by 10 gives me 2 amps. It's that same calculation. 20 volt divided by 10, 20 volt divided by 10. It's 2 amps in each one of these branches, right? I said when I did the calculation earlier, my 20 volts and my resistance total of 3.33 comes out to 6 amps. Now, does that make sense? If I had 6 amps leaving my main circuit, I get to this point. We said 2 amps go through R1. Well, that means that 4 amps are headed toward R2 and R3, right? 2 and 4, does that equal the 6 that came into that node? Absolutely. I get to this node. I had 4 amps that was continuing this direction. We know that it's equal current because the resistance values are the same. So I've got 2 that goes through R2. The other 2 go through R3. and then they just combine on the other side. 2 and 2 gives me 4, and then 2 and 4 give me 6. And so it all works out. When we talk about Kirchhoff, that's what we're looking at. We're looking at, remember what Kirchhoff said about current. He said that current, the current going into the node equals the current leaving that node, right? Whatever goes in here, 6 amps, must equal what comes out, 2 and 4, or 6 amps. And we can do that at every point, every node along the circuit. We also look at power. The power across R1, power is equal to voltage times current. We said our current was 2 amps. Our voltage is 20 volts. So 20 and 2 amps gives me 40 watts. Same current through each one of these resistors. Voltage is common, so therefore, once again, 20 times 2 is 40 watts, and 20 times 2 is 40 watts. We can add our wattage up for 120 watts. We can also go over and just verify that, do the calculation. And if we look at our total voltage applied, which was 20, and we look at our 6 amps of current, so 6 times 20 gives me 120 watts, right? 40, 80, 120. 40 watts, 80 watts, 120. So it all works out. Questions about those calculations? All right. All right, so here, I work in circuit with voltage. So we've got 10 volts. We know that this is a parallel circuit. We know that voltage is applied across each one of these circuits, or this 10 volts applied across each one of these resistors. Now, here's what we could, in some ways, we're kind of working just a different order based on what we know, so that we can avoid that whole reciprocal of the sum of reciprocals. We know right now that this setup, this parallel setup, doesn't fall into either one of the 2 shortcuts that we have, right? It's not equal resistors, and it's not just 2 resistors. And so we can't use product over the sums, that'd be 2 resistors, and we can't use resistance divided by the number of branches, because they're all different values. And so what we can do is take what we know, and instead of jumping into that reciprocal of the sum of reciprocals to calculate my total parallel resistance, we'll just take what we know and work off of some easier calculations. Now, what do we know? Well, we know that this is a parallel circuit, and that there are 10 volts applied across R1, 10 volts applied across R2, and 10 volts applied across R3. Now, since I know the voltage and I know the resistance in each one of those branches, it's pretty easy for me to, at that point, calculate the current through each one of these branches, right? I can say that the current R1 is Ohm's law says 10 volts, because I had 10 volts across R1, divided by the resistance, 10 ohms, or I get 1 amp, right? Everybody see that? We've got 10 volts across R1, divided by 10 ohms gives me 1 amp of current through R1. Now, do the same thing with R2. What's the voltage across R2?
Ten votes.
10 volts, right? Parallel circuit, voltage is common in parallel, so it's 10 volts. Well, if I've got 10 volts and I'm going to calculate the current, 10 volts divided by 20 ohms, right? I can reduce that down. 10 over 20 is 1/2, or 0.5 amps, right? Or how would I say that in engineering notation if it's 0.5 amps?
500 milliamps.
500 milliamps. Very good. Absolutely. Remember, we don't like to start off with that decimal, so we want to move it. We move it 3 places. So that's times 10 to the negative third, 500 milliamps. Same thing with R3. You know, I know my voltage, 10 volts. I divide that by my resistance of 30. You know, 10 divided by 30 gives me this 0.33 amps or 330 milliamps, right? And so what I just did is I just calculated the current in each one of these branches without going through the process of, you know, working through that reciprocal of the sum of reciprocals formula. You know, not without having to get to total resistance. But since I know the branch currents, right, 1 amp, 500 milliamps, 330 milliamps, now I also know my total current, because that total current, it leaves the supply and then it separates out. And so if I just add all of those currents together, those branch currents, they all originate here with this supply. And so therefore, you know, 1 amp plus 500 milliamps plus 330 milliamps is going to give me this 1.83 amps. 1.83 amps is my total current. 1.83 amps. And if I really wanted to get to it, you know, if the question at the beginning had been, what is the total resistance? Well, now I can get there because I have Ohm's law that says that my resistance is equal to voltage divided by current, right? If I take my 10 volts and I divide it by my 1.83 amps, my 10 volts divided by 1.83 amps is going to give me 5.54 ohms, you know, which I was able to get there without having to do the reciprocal of the sum of reciprocals formula. I was able to just take what I know and work back toward the total resistance. Now, does it meet our criteria? 5.45 ohms, smaller than the smallest branch resistor, which was 10. Absolutely, right? So it does meet that criteria. Now, that doesn't necessarily mean that it's always correct. You know, you could still make a mistake and it be smaller than the smallest resistor, but usually that's a great check, especially if it's a math issue. Usually you've moved the decimal one too many places, or you know, it's going to indicate you made a mistake somewhere. All right. Questions about that? You know, really, usually when you're asked the question, you're not asked the question about total resistance, and so typically, you know, you wouldn't even make the last step unless you just had a chart you had to complete. You wouldn't even make the last step for total resistance. You'd be, you know, looking at some of these individuals, and then maybe a total current. You know, they may ask you about what is the total current. And yeah, you could get there if you did the reciprocal of the sum of reciprocals, right? If you took 1 over 1 over 10 plus 1 over 20 plus 1 over 30, you go through that process and you could calculate your total current. But you can also do that based on what you know, knowing that voltage is common in parallel circuit. And so therefore I've got 10 volts across each one of these resistors. I already know the value of each one of these resistors. I can calculate the current in each branch and then add those together for my branch, my total current. So there's multiple ways to get there is what I'm saying. And that's always nice because you can use the other method as a check. Same formula or same schematic. We're looking at power. If I wanted to calculate power, you know, you can use the formula P is equal to E squared over R, right? You know, I could go in and I could talk about the voltage. I already know the voltage drop across each one of these. So I could take 10, square it, and divide it by 10. And that's going to give me my wattage, right? 10 squared would be 100 divided by 10 would be 10. So you can see I'm going to get 10 watts across R1. You can do that. like I said, however, some people, I think they feel comfortable at least with the formula. It's just a matter of making sure you get the formula right. It's always easy to remember this one: power is equal to current times voltage. Well, you can do the same thing. It just means that you're going to have to calculate your current, your branch current, and then use that current by your voltage across R1, right? And so for if we look at what we calculated, 1 amp, we said it was 1 amp. 1 amp times 10 volts is going to give me 10 watts. We said this was a half of amp, or 500 milliamps. So 500 milliamps times 10 volts is going to give me 5 watts. And then we said that this was 330 milliamps, the current through this branch, times 10. So which means I'm really just moving the decimal. I get 3.33 watts for a total of 18.33 watts, right? When there's an open in a parallel branch, the R total will increase because the open is very high resistance, right? And so let's just see if so what they're saying is, you guys know, bear with me, it's not the easiest drawing tool here. I think this is a way to kind of capture some of what it's saying. All right, so let's say that I had those two resistors, and this one is a 10 ohm resistor, and this one is a 5 ohm resistor. Without getting into any detail in terms of specifics, what can you tell me about R total just based on those two resistors? R total is going to be what?
In
It's going to be what?
10.
10. Okay, so two resistors in parallel, or any resistors in parallel, we said that R total will always be smaller than the smallest resistor, right? So if I've got these two resistors in parallel, my R total is going to be smaller than 5 ohms, right? That makes sense? It'll always be smaller than the smallest resistor. Now, what this is saying about an open, let's say that you had, let's see how much this erases, right? A little more than I wanted. Let's say instead of having that 5 ohm resistor, now you have, 5 ohm is still there, but you got an open. There's no path for current to flow. So it's like this doesn't even exist in terms of your circuit. And so now what happens, what they're saying in this top section here, in terms of very high resistance, an open is going to be extremely high, almost infinity in terms of resistance. There's no path for current to flow. And you can see how our circuit, and just that basic rule in terms of the R total is always going to be smaller than the smallest branch resistor, would go from 5, which was the smallest, to an open. So now it has more than doubled, because it is going to be, resistance total now would be 10 ohms, because you're only left with that 1 ohm resistor. And so when it says an open very high resistance, what it's talking about is this this value here is going to be very high in resistance. When I get an open, that means no path of current to flow. Means extremely high resistance is the same thing as this no path for current to flow. I mean, so much resistance that we don't have current to flow, right? And what impact will that have on R total? Well, it's going to cause R total increase. You know, whatever it was before, it's going to go up. Now, if you had, 25 resistors in parallel and you lost one of those resistors, your R total, it may not go up by much. It's not saying that the circuit resistance, the total circuit resistance will be infinity. It's not saying that. It's saying that that branch will be infinity. And so now you're basically calculating the R total based on the branches that are left. And so you can guarantee that the resistance is going to go up. Anytime you lose a branch, your R total is going to go up. Now, the opposite of that, let's say, for example, that instead of losing a branch, let's say that, something happens and you get a short. Well, a short, very little resistance, right? And even though it looks like, wait a minute, this short is after that resistor, but keep in mind, these are basically equal potential points, meaning they're in terms of electrical resistance, they're basically the same point. There's very little resistance in this wire. And what's going to happen is these electrons are going to take the path of least resistance. And so they're all going to run down this short because it provides almost zero resistance, very little resistance. And you're going to see this circuit all of a sudden, it's going to, your current through this resistor is going to decrease because it's all taking this other path, this shorted path. And so you're going to see your R total, which is smaller than the smallest resistance, right? And now you've got a path that's got a resistance of almost zero. So your R total is going to go to almost zero. So with an open, R total is going to increase. Doesn't mean it's going to increase to infinity. It's just going to increase. It's really based on the number of branches and the other branches that you have. So if you have an open in a branch, you'll get very high resistance in that branch. R total is going to increase. If you get a short, and so now you've shorted across a parallel circuit, well, you're providing a pathway that's 0 ohms. And so therefore your R total, which is smaller than the smallest, is now going to go to basically 0. Questions about that? Okay. All right, so a couple of questions for parallel circuits. How many paths are there for current flow in a parallel circuit? I can barely hear you.
However many circuits there, like,
So more than one, right?
yeah, it depends on however many branches you have. If it's just one, then it's not really a parallel circuit. It's just a circuit.
Right.
So it's got to be
Right.
2 or more.
2 or more, absolutely. There could be any given number. By the way, I could hear somebody barely speaking in the background. So I'm not sure if somebody else was trying to give an answer. I could just barely hear you. What's common in parallel circuit?
Voltage.
Voltage is common. Voltage is common. Absolutely. We'll come back to it. What is the formula for calculating R total in a parallel circuit where each branch has a different resistance? So if each branch has a
Reciprocal
different
of
resistance,
reciprocal.
absolutely. So the reciprocal of the sum of reciprocals, absolutely. So it's at 1 over 1 over 1, 1 over 1 R1 plus 1 over R2 plus 1 over R3. Absolutely. Yep. Very good. Now, well, I think they're asking that the next 2 questions. What is the formula for calculating R total in a parallel circuit where each branch has the same resistance? So if all the resistors are the same.
Is that the one you do the ratio of? Or you divide it by the 3?
Yes. Yes. So if all the resistors are the same in the parallel branch, then all I have to do is take whatever that resistance is, and divide it by the number of parallel banks, right? Parallel branches. And so if it's, I think we had, 10 ohm resistors. If we had 10 of those in parallel, then I could take 10 ohms divided by 10 and I get, R total of 1, right? I'm just taking the value of the resistor and then I'm dividing it by the number of resistors. What's the formula for calculating R total when in a parallel circuit when you have two branches with the same value resistor? So I don't know if that question is asked the way I think they mean to ask that. What's the shortcut whenever you have two resistors in parallel?
You get the smallest resistors number.
Divided by 2.
So with the way this is asked, yeah, it if I've got two same value resistors in a parallel circuit, then I would take that value and I would divide it by 2. Yeah, so whatever it may be. If it was 10 and 10, I divide it by 2 and get 5. Absolutely. Now here's what they were really prodding you for, and the question's a bad question the way it's worded. If I have two resistors in parallel, they could be the same value, but typically I use this formula whenever I've got two resistors in parallel that are differing values. Let's say I had a 10 and a 20 ohm resistor, then I can use the product over the sums. I take 10 times 20 and say, okay, well that's 200. And then I could divide that by 10 plus 20 divided by 30. So 200 divided by 30 would be my answer for my total resistance, that product over the sums method. All right, so let's see what we can do here. All right. They went ahead and they gave you our total. Our total was 10.9, which, that seems like it could be right. 10.9 ohms. And wait a minute. All right. Well, they went ahead and they gave you everything, right? So that's mighty nice of them. Yeah. Let's see if it makes sense. R1, R2, and R3 are in parallel, so therefore we know that voltage is common. This 10 volts across each one of those. You can see that R1, R2, and R3, 10 volts. They then calculate the current through R1. 10 volts divided by 20 ohms is going to give me half amp, or the way we should do it in engineering notation, 500 milliamps. Current through R2, it's the same 10 volts divided by 40 ohms. That's going to give me 250 milliamps. And then the same 10 volts divided by 60 ohms, which works out to 166 milliamps. I add all those together, I get 500, 250, 166 for 920 or 0.92 amps, 920 milliamps. And then I can also calculate the wattage. It's just a matter of the current through each one of these resistors times the voltage, which is common in parallel. So all times 10. You see 5, 2.5, 1.66 watts, total 9.17 watts. And I guess it's supposed to make it more impressive that it's in red because they just gave it to you. Let's try this one. That's not the same circuit, is it? 10, 40, 50, 60. No. All right, so let's try that one. Let's see if we can calculate these values over the next, it's about 8 minutes. What'd you guys get for R total?
10.
10. Okay. Anybody have anything else?
It was less than 40.
Yes. Yes. Less than 40. Absolutely. And you know, you check that 10, you go, well, okay, that's less than 40. Let me ask you this. Did anybody not start with R total? Yeah, you didn't have to start there.
Is it 15 or is it 10?
No, I think it's 30. It's 30.
Not- you think it's 30?
Yeah, I didn't add them all back up.
So if we take, you know, 1 over 40 plus 1 over 50 plus 1 over 60, that's going to be 0.25 plus 0.2 plus 0.167. So I get like 16.2. But this proves my point. Sometimes that is the hardest part of the entire circuit is our total, because you have to deal with those resistance and that crazy formula, the reciprocal of the sum of reciprocal. So let's go around that, right? Let's skip R total. What's the voltage across R1?
10.
10 volts. How did you calculate 10 volts?
What shows it in the formula? 10.
It's the
So
same.
it's-
The voltage is the same across the parallel.
Absolutely, right? It's a parallel circuit. You know, it's 10 volts. So voltage R1, voltage R2, voltage R3, all 10 volts. Bam, we've got 3 answers already correct. Now, current. How am I going to calculate current in R1? So our next, calculation is current R1.
10 divided by 40.
10 divided by 40. Absolutely. 10 divided by 40, that's what, 0.25? So 0.25 amps, or if I annotate that in engineering notation, 250 milliamps, right? Same thing with R2. If I'm going to calculate the current in R2, same 10 volts. Current is equal to voltage divided by resistance. Now I've got 50 ohms. And so my current is 10 volts divided by 50, or
0.2.
0.2. Absolutely. 0.2 or 200 milliamps. Yep. And then the same thing with R3, 10 volts divided by 60. And so it's, what'd you guys get for that?
0.16.
Yes, 0.16 amps, or 160 or 166 milliamps. What about R total? I'm sorry, not R total. Current total. What about current total?
0.61.
0.61. Now, how did you get that? How did you get your? Because we skipped over R total, and so now we're dealing with the totals. We've got our total voltage. We don't know our total resistance, but you've calculated my total current. How did you get total current?
Just the sum of the 3.
Sum of the 3, right? It's not that hard. So you added those up, and you got 0.616 or so, or 616 milliamps, somewhere in that ballpark. Then your powers, you already know branch currents now, right? And since I know my current in each branch, and I know power is equal to current times voltage, it's real easy for me then at this point to go in and calculate the power across R1. So what did you get? Power R1,
2.5 watts.
2.5 watts. Very good. Very good. How about power across R2?
2 watts.
2 watts. Power across R3?
1.6 watts.
1.6 watts. Very good. Absolutely. And then total power.
6.1 watts.
Okay, 6.1 watts. So, you know, we can calculate everything here, even without our R total. Now, what we could do at this point is we could go back and we know our total voltage and we know our total current, right? We said our total current was 0.616 amps. And so voltage divided by current equals resistance. So 10 divided by 0.616 should give me, you know, whatever that total resistance is. And I think it's right around 16.2, somewhere around there. Very good. Yeah, 16.22 is what they have. Awesome. You know, just to make sure that things make a little bit of sense, you know, we know that voltage is common in this parallel circuit. So each one of these branch resistors has 10 volts across them. We know that. The current, you know, we know that current takes a path of least resistance. And so my current across my smallest resistors should be greater than my current across the other resistors. And so I got 0.25 amps, 0.2 amps in R2, 0.17 in R3. And so you can see as my resistance is increasing, 40, 50, 60 ohms, my current is decreasing. You know, it went from 250 milliamps to 200 milliamps to 170 milliamps, right? And so that's what we would expect. You know, same thing with power. You know, I would expect my power to be the greatest where I have voltage with the most current. You know, power is equal to voltage times current. Since voltage is the same across all three of these, where I have the most current is going to have the most power. So in other words, where I have the most current is also going to dissipate the most heat, right? Which makes sense. And so, you know, R1, we're looking at 2.5 watts, R2, 2 watts, R3, 1.67 watts. All right, very good. Any questions about that? Okay.
No, not right now. Sir, you said they're going to look into getting the page to where we can log into it again.
Yeah. I tried to log into it over the break and it was not up yet. And so I'm going to have to reach out to.
Yeah, it wasn't when I tried to just now.
Yeah. Okay. I'm really surprised it's been down that long. So I'll reach out and see what I can find out. I would expect it will be back up very soon. Now I will say, oh man, you know, and I did not even think about this, and I'm not. This is going to be a learning experience for me because I'm not 100% sure where that server is located. I think I might know where it's located, but I did notice as I was coming across town, there was a wreck and one portion of town was without power. Now I can imagine they're still without power, but it might be a power outage that is causing that.
Where that server is hosted?
Yeah. I wonder if that's the case because there was, I mean, it was about 3 blocks. And I know the technology company used to be in that area. I'm not sure they're still there or not. And so, but yeah, I mean, they had cops out that were directing because stoplights were out, and yeah, that just hit me. I bet that's what it is. I'll let you know. All right. Any questions about series or parallel circuits? Now, what we're going to do, we're not going to do it tonight because obviously we're getting short on time. But what we're going to do is we're going to take series and parallel, and then we're going to smash them together, right? And so we're going to have series parallel circuits. And before we completely freak out and think, oh my gosh, what do I do? We're going to be able to go in and just like we heard in the video where you can go back and redraw, we're going to make some sense out of these circuits. And it's not that you'll do this and when you get a schematic, it's impossible for you to take a schematic and reduce it down to, oh, let me get my total voltage and my total current. And it's not quite as simple as we make it here. But we're learning the principles so that we know as we see voltage dividers, as we see, by the way, if a group of series resistors is called a voltage divider, right? It takes that voltage, current's the same running through those resistors, and we can tap off different voltages based on where we measure. If that's a voltage divider, what do you think a bank of parallel resistors are called?
Voltage amplifier.
Oh man, that's a good guess, but no. If we take in a series circuit,
dividers.
what is it?
Current dividers.
A current divider. Absolutely a current divider. So we take a series, a group of series resistors, and now we can tap off and get different voltages. Well, if we take if you look at what's happening with banks of parallel resistors, they've got the same voltages across them, but we've got different currents, right? And so we could tap into any of those currents that we might want to tap into. It could be a current divider. And so long story short, we're going to take these series resistors, series circuits, these parallel circuits, we're going to slam them together, and then we're going to start working to solve and break down these circuits so that we can make sense of even what a series parallel circuit entails, what it looks like. So that's coming for us next class period. All right, we're at a quarter till, and so this is where I'm going to go ahead and end class here and open it up. If you guys have any questions, I'll be on the line for the next 15 minutes or so. Feel free to ask. Otherwise, I hope you guys have a wonderful night, and we'll see you on Wednesday.
Thank you again.
Absolutely. Thank you.
I had a question.
Sure, Martin.
I was going through the things when it was up last week or so. It said, did we go over algebraic expressions?
So we went through, I can't say that we hit every one of those first presentations. We went through, obviously, a bunch of the math. Is there any questions that you had, specific questions you had about the algebraic expressions?
No, well, just what was the production and dependencies of the stuff?
Yeah, the proportion and dependencies.
Yeah, because
we talked about that a little bit, and that was really making sure that we knew what we were talking about when we were talking about directly proportional or inversely proportional. And the reason that's important is when we're talking about Ohm's law, voltage equal to current times resistance, to be able to determine what is directly proportional and what is inversely proportional. So current and voltage, those two are directly proportional. As one goes up, the other goes up, right? Okay. If I apply more voltage to a